Session 2 of the FIJI for Beginners workshop, we're going to cover preparing your image for publication, presentation of 2D data, 3D data, and time-lapse data. Activity 10 is adjusting the brightness and contrast within an image. So again, we're going to use this for visualization purposes only, just to make the data within the image a little bit clearer. For our example, we're going to use the zeiss.lsm image. Again, this has 3 different channels. What we're going to do is convert the lookup table that's in here to something called the high-low lookup table. So in this case, that's here, high-low. So what the high-low lookup table is doing is it colors 0 intensity pixels as blue, and any saturated pixels as red, and there's grayscale in between there. So you may be able to see a little bit of blue intensity in the background here, and at the moment we don't have any red intensity within the image, which is good. It means the data wasn't saturated when we acquired the image. Okay, so to adjust the brightness and contrast, we're going to go to Image, Adjust, Brightness and Contrast, or Control-Shift-C. Here we've got our intensity histogram, and here are our maximum and minimum values. So you see, if I move the minimum value in to the right, we're going past the data, we're actually starting to clip information. Okay, so again, you want to be very careful about doing that. On the maximum side, if we decrease this down, you'll see we'll come to a point where we start getting red pixels where we're actually saturating the image. So this image looks like it was taken with pretty much most of the dynamic range. One thing to be very wary of when you're using the brightness and contrast, I know a lot of people use the auto function. You can see it does some very strange things to your image quality, so be very, very careful about using the auto function. Here we're going to reset. So we can bring this down to a point where we're starting to get a few red pixels, and then bring it back so we don't have any red pixels. Once you hit apply, it's going to rescale between these 2 points, these minimum and maximum points, across your full 16-bit range, for example here. So you can apply here, and now rather than using the high-low lookup table, you can put it back into whatever lookup table you wanted. You can do that, go through, move to the next channel, repeat the process, using the high-low to allow you to move the minimum and maximum positions, hit apply once you're happy, put the lookup table back to the correct color, and then move on to the next channel. Activity 11 is calibrating images. So what we're doing in this activity is to add some kind of distance information into an image that hasn't carried across that information from the microscope, so it's an uncalibrated image. In this example, we're going to open up like a triple merge uncalibrated.tiff. If we open this up, you can see in the top left hand corner here it has no distance information, so it's only giving us pixels. We can modify this afterwards if we know what the pixel dimensions are. We do that by going into FIJI Images Properties, or Control-Shift-P. And this tells us the properties of the image. So for example here, we've got 1 channel, 1 Z, 1 frame. So this is an RGB image. Our current unit of length is in pixels. We can change this to UM, which FIJI will recognize as microns. And in this example, we want the values to put 0.031678. If I hit the global button here, that will apply that to all images that are open within FIJI. So be very careful using that global button. Once I hit OK, you'll see we've now got physical distance of the image as well as the number of pixels that image is made up of. One of the questions we regularly get is, how did I know what the pixel size was to be able to calibrate that image? So there are special slides available, which if you're at the Melbourne University, we can help you with, which will allow you to measure distances on your microscope. The other way of doing it is using something like a hemocytometer slide, like this on the right-hand side here, which has defined distances. If you can capture that distance information in the exact same way you acquired your data, we can then work out the distances and the sizes of the pixels. So in that case, we'd use the line region of interest tool and draw that across our distance. That will give us the length in pixels. And as long as you know the distance, you can then work out the size of the pixels within that image. One other example of this is when we have an image which has a scale bar already written into it, but we don't have the distance information within the image. In this case, we can again use the line region of interest tool to measure the length of that scale bar. So I'm holding Shift, left clicking and dragging across the length of the scale bar. We can see in the FIJI window that says that's a length of 182 pixels. So we can use the scale information in the image of 101 microns to work out the pixel size. Activity 12 is adding a scale bar into your image. So again, allowing people who are looking at the data to have some kind of context in terms of what the distances and physical sizes within the image are. So now that we've calibrated this image, we can add a scale bar onto the image. So again, we're going to use FIJI, Analyze, Tools, Scale Bar. This brings up a very similar dialog box to the calibration bar. We can change the width in microns. Obviously you want to make something that's makes sense for the size of image that you have. You can change the height in pixels. Again, try and make it look a little bit like a bar. You can change the font size, font color, any backgrounds. Again, the position into the four color corners, and also at a place of your own selection. Again, untick overlay. I very often save a version without the text and a version with the text. And I always save the scale bar length in my file name, so I also know what the scale bar length is as well. Once you hit OK here, that's again going to be burnt into your image so that you can then get rid of it. And then obviously File, Save As, TIFF. In activity 13, we're going to show you how to build a 2D data panel. So a panel of 3 channels, individual channels, and then a merge at the end. So we're going to use a lot of the functions that we've learned so far in the workshop. To do this, we're going to open up this bpae.tiff image. So this is the merge that we're going to use. And what I want to do initially is to duplicate this image. So I'm going to right click, hit duplicate. I don't mind the name, so we'll just go ahead with that one. We're then going to generate the individual panels by splitting this RGB image out. So hopefully you remember image, color, split channels. This is now giving us the 4 different images that we want to use to build up our panel. Now you could go in and assign a lookup table to these and have them as the individual colors, but as I mentioned in the presentation, the grayscale is quite a good way of presenting individual channel information. So we're going to keep this as grayscale data, but what we're going to do is convert them from 8-bit into an RGB image. So RGB, we'll go through and do that for each of the channels. Okay, so all of our data now is in RGB. So what we want to do now is convert these 4 images into a stack, so bring them all together. We're going to do that under Image, Stacks, Images to Stack. Okay, we'll just give that the name stack, and we're going to close the source images. Okay, so now we've got a stack with 4 images. We've got the merge at the start, followed by the red channel, followed by the green channel, followed by the blue channel. Now obviously that's not the correct order that we want those in, so we're going to have to go through and change those. And we're going to go back and use Image, Stacks, Tools, and we're going to use the Stack Sorter tool. Okay, so here we've got buttons, assign the currently selected image to first, so this is our blue channel, so we want that to be in the first position. Our next image is the merge channel, we want that to be in the last position. So we can go back, got our blue channel in the first position, then it's our red channel, followed by our green channel, followed by our merge channel. So maybe we want to change the order of the second and third images in these stacks. So I can just move this one on one. And now we've got our DAPI, our green channel, our red channel, and then our merge channel. And now we're ready to put those together into a panel for our figure. And again, we're going to do this under stacks. So image, stacks, make montage. Okay, so our montage allows us to define, obviously we have 4 images. How are we going to lay that out? We're going to have it in a column of 2 by 2. In this case, let's go with column 4 and row 1. Scale factor is downsizing at this point, so we want that as 1, so we want as high quality as possible. We want to include all of the slices. We want an increment of 1, so again we want to include all of the slices. And border width will draw a line between the images. Let's put that to 3. And if we hit OK, we should have our finalized panel. Again, that's already RGB, so we can just quickly save that out as a TIFF file and use that in whatever software you want to export it out into. One other way of presenting 2D data, if you don't want to make the panels yourself, is to use a plugin within FIJI called FIJI. This requires you to add 3 download sites into FIJI, and there are further instructions on this website if you want to work out how to use this. Now we're going to look at how to present 3-dimensional data in either a 2D format or using a movie for presentations. The first activity that we're going to use is activity 14, and that's creating something called a Z projection. So taking all of that 3D data and compressing it into a 2D image for either a lab presentation or to print out and put into your lab book. So for all of the 3D data, we'll be using one of 2 files, either the omx3ddata.tiff or the kidney3ddata.tiff file. So let's drag and drop one of those in. We'll see that I've already created these as RGB files. These have 3 channels in there, so we've got the blue, green, magenta setup. Hopefully you guys would know how to get to this point. And this is a Z stack running through a kidney tissue section. So the problem is, how do we present all of this data in a 2D format? So to do this, we're going to go to Image, Stacks again, and we're going to go to the Z project function. Alternatively, we also have a stack shortcut up here, which we can also use to select Z project. This gives us a dialog box saying, do we want to include all of the slices within the data, and also a projection type. Now what we have to think about when we're looking at this is that the different projection types might work differently or better for different types of image samples. The best way of working this out is to go through and just try them one by one and see which one you think presents your data the best. So what we're looking at is each pixel down through Z. If we're using average intensity, then the final image that's plotted will have an average of all the intensities that are running through there. So in this example, there's quite a lot of black backgrounds or out of focus from kind of image 26, between 1 and 26. So if we used average here, it might not work very well. We can always go in and say we want to start at image 27 and let's use, for example, the maximum intensity. Okay, so that's a representation of all of the data that's included within that Z stack. So the activity here is to go through and play around with the different types of Z projection techniques and work out which one you think works best for presenting the data for the kidney section and also for that OMX 3D data.tiff image as well. Activity 15 is another way of presenting 3D data in a 2D format. In this case, we're using both top-down and side views of the volume information in something called an orthogonal viewer. For activity 15, let's continue with the kidney 3D data.tiff image. And in this case, we're going to use the orthogonal viewer. So again, we can use image, stacks, and in this case, we're going to use orthogonal views, which is Control-Shift-H. This, in addition to our normal Z-stack viewer, gives us these side panels. So you can see the panel on the right is giving us a YZ projection of the data, and the panel at the bottom is giving us an XZ projection of the data. The little crosshairs allow us to move around within the data and inspect what we think, or the regions that we think might be of interest. We can also scroll through in Z. Once you're happy that you've found a position that you want to present, you can go ahead and save the individual panels. So let's take this one, for example. Click Save as TIFF. And when the data is finally saved, it doesn't have these yellow lines on it, so you just see the side panel views. So again, a very useful way of presenting 3D data. This normally works very nicely if the 3D data that's being presented is more kind of cubic in shape, rather than these kind of thinner Z stacks that we're presenting here. Activity 16 is showing us another way of presenting 3D data in 2D. And in this case, we're going to use the montage tool that we used earlier on to make our 2D panel. For this example, we're going to use the OMX 3D data.tiff. And again, I've made an RGB of the two channels here, so we've got green and red channels through 54 Z slices. Okay, so let's go through image, stacks, make montage again. Now, let's use the default settings here. If we click OK, if I make that a bit larger, hopefully you guys can see it's very difficult to see any of the data within that montage. So there's way too many panels going on, the lines between them are too thick. So let's go back and let's modify how we're presenting that data. Make montage. In this case, let's not present all of the data, but let's show some representative slices through that 3D volume. So for this example, we're going to use 3 columns and 3 rows. We're not going to downsample the data, so we can still see it at its highest resolution. We're going to use all of the slices, so 1 to 54 in our increment. we're going to set to 5. So we're only going to present every 5th image here. Border width, we can keep it 3. And now if I click OK, hopefully you guys can see that that figure is a little bit less busy. Yes, we don't have all of the content, but it's a lot easier to decipher what's going on within that image. Again, we can save that out as a TIFF file for use for making a figure. In activity 17, we're going to present this 3D data now not as in a 2D format, but as a movie. And the first example we're going to do for this is something called a Z translation. So, for activity 17, we're going to use the kidney 3D data.tiff image, and we're going to present a Z translation. So basically just us, a movie of us scrolling down through the focal planes, like this. Now you'll notice in the bottom left-hand corner here, there's a little play button. If we press play, you'll notice that it automatically starts to scan through that Z stack information. I see again we've got the problem at the start where there's a lot of out of focus Z planes. We can clip those out of our image as well. Okay, so if we want to play around with these settings, we can right click on here and it allows us to change some of the parameters. So for example, we can change the speed that we're playing the image at. So for movies to scan fairly cleanly through, you want to have at least kind of 10 frames per second, more like 15 to 20 ideally, but that kind of depends on the number of Z stacks that you have within your image. For our image, if you remember, we've got all of that empty information at the start, so we can go from first frame from 27, and the last frame, probably the last 10 frames there isn't any information either, so we can have the last frame as being 110. Now if we go through, we can scan through the data. Once we're happy that we've got the correct file, make sure you hit the pause button here so it doesn't continue playing, otherwise your computer will alarm at you incessantly. And now when we're saving the data, we're going to file, save as, we're going to save it as an AVI rather than as a TIFF file. Okay. Really important thing here is don't put any compression on. If you put compression to none, then you can then export it out and convert it to whatever file format you want for playing on your computer. Again, you get the chance to put in the frame rates, hit OK, and then you give it a chance to give it the file name and save it where you want it. In activity 18, we're going to again show the 3D data in a video format, and in this case we're going to use FIJI to do a very simple rotation around one of the axes. For this example, we're going to use the OMX 3D data. So again, you can see the two channels down through Z. In this case, we're going to use something under the stack window, which is called 3D project. Okay, so again, you can play around with some of the parameters here. For example, the axis of rotation. Slice spacing is the step sizes that your data was acquired with. So this is a SuperRes data set, so it was acquired with step sizes of 120 nanometers. In this case, we're going a whole 360 degrees, so 0 to 360, and we're doing it in 10-degree increments. We're going to end up with 36 frames to go through that 360 degrees. I'm going to show you quickly what happens if you don't hit the interpolate button. You will see a problem with the data that's generated. So let's click OK. You'll see it's going through those 36 rotations. And now if I make this image a little bit larger, if I hit play, you should see a problem when we hit the side view of the data. Yeah. So FIJI isn't working very well in terms of putting together this data set in that Z direction. So we don't want to show a video like that. So let's go back to the stack menu and do that again. Where are we? 3D project. In this case, we're going to hit this interpolate button and hit OK. So there's the exact same settings apart from that interpolate button, and hopefully you'll see now that the movie that we generate looks much, much better. So FIJI is just filling in the gaps, that missing information in between those Z. Again, we've only got 36 frames here, so at 10 frames a second, it's only taking 3.6 seconds to do the rotation. That might be a bit quick for what you need, so you might want to go to 7 frames a second, slow it down a bit. The key thing here is you need enough time to talk about the biology as the movie is playing. Yeah? And obviously you don't want to make your audience sick as well. Once you're happy that you've worked out what your frames per second are, again, we're going to go in File, Save as an AVI, with no compression. Let's stick with the 7 frames a second, click OK, and then we can save that data. FIJI also has a 3D viewer plugin which you can access in the plugin menu. This allows you to zoom, rotate volumes and take snapshots. It also allows you to record rotations and custom movements into movies. You can also show the data as a volume, as orthoslice and surfaces. There's more information on this web page. We tend to tell our users that if they're wanting to do more advanced 3D movies, then a software like Amaris or Velocity is much better set up for doing these types of movies. Indeed, Amaris have just released a free Amaris viewer which allows you to do rotations and snapshots, which will be much higher quality than what you can get using the 3D viewer plugin. So we're on to the last stretch. So we've covered how to present 3D and 2D data. Now we're going to look at how to present some time-lapse data. Activity 19 is how to show a simple movie of time-lapse data. For this example, we are going to go into the erlive.tiff image. Just rescale that so it fits the screen. And in this example, this is live cells, 100 frames of an endoplasmic reticulum stain. And you can see the cell over time. The endoplasmic reticulum is fairly dynamic. So we want to present that as a movie. Now we've already kind of done this with the Z translation. We can right click on the play button and play around with the frames per second. You might want to go back to 10 frames per second, for example. The other thing we can do is go in and change the lookup table as well, convert it to an RGB, and then again, file save as AVI with no compression, and save that file to where you want to. There is one issue though with the movie that we're creating here. So similar to when we were adding the scale bar to give distance information and calibration bar to allow people to interpret the colors, we have no idea of how long this movie lasts for and what each of the time points are. So we need to annotate this movie to allow the people watching understand the time lapse of the actual acquisition. So activity 20 is annotating movies. So I know, for example, that these images were taken every 4 seconds. So to label this, we're going to go into Image, Stacks again, and we're going to find the Label button. And in this case, we can play around with the formats. We can play around with the interval, as I said, that's 4. Let's go with this. Text, so I know it's seconds. And the range, we definitely want to include all of the time lapses. In this case, We're just going to hit OK with this. And you can now see up in the top left hand corner here that we have some information about how long this movie actually lasts for. If you play around with the formats, you'll get different layouts in terms of what this looks like. Again, this can then be saved out as an AVI file, no compression, and saved where you want on your computer. Okay, we've reached the end. This is the last activity, and this is showing time-lapse data in a 2D visualization using something called a Kymogram. So activity 21 is using a Kymogram. So for this, we're going to use the images in the Kymograph folder, and we're going to open tracking.tiff. And you'll see in this example, if I play this, so we've got two sets of organelles that are tracking along a neuronal process, and what we want to do is work out which ones are moving to the right, which ones are moving to the left, and which ones are staying static over time. Okay, so what we're going to do first of all is to split the channels. So hopefully everyone remembers how to do that. Image, color, split channels. Now we have channel 1 and channel 2. Next we want to use the line tool, just the straight line. And I'm going to left click and I'm going to hold shift at the same time to make sure that this is a straight line. I can release. And the next thing I want to do is reassign this region of interest onto the other one. So if we remember, edit, selection, restore selection, or control shift E. So we've got the exact same line on both sides. So let's go back onto channel 1, and we're going to run a Kymogram on channel 1. So to do that, we're going to analyze multi-Kymogram, multi-Kymogram. And that's going to ask us what is the line width that we want to use. In this case, we're going to use 29 pixels, so we're making the line pretty much the full length of depth of the image, height of the image. This has to be an odd number for this to work. So let's go through and do that. And this has generated our Kymogram. So what we've got along the x-axis is intensity across this line, and in the y-axis is time. So any organelles that you see going straight down or not moving over time, anything that's moving down to the right is moving to the right over time, and anything that's moving down to the left is moving to the left over time. So let's just rename this red, just so we know that that's from the red channel. And let's repeat the Kymogram on the channel 2. So analyze multi-Kymogram, multi-Kymogram. Again with 29 pixels line width. And here we've got our green Kymogram. Okay, so we could keep these separate, but we can also merge them back in together so we can see both of the organelles in one 2D image. And to do that, we're going to use the image, color, merge channels. And our green is going to be the green Kymogram, and our red is going to be the red Kymogram. We don't want to create a composite. Let's keep the source images. Okay, so in this example now we've got a Kymogram showing what these organelles are doing in 2 channels over time. So again, not very quantitative, but a good heads-up display of what's happening to these organelles over that line over time. And again, you would save that out as a TIFF file. That brings us to the end of the demonstration part of the workshop. We now have free time for you guys to go through and try all the activities that we've covered. You will find those in the hands-on session PDF that you should have downloaded along with the demo data. As mentioned before, we have multiple members of our team online waiting to answer your questions if you have any. Please use the chat box to raise if you're having any problems, and I'll set you up in a one-on-one breakout room with a member of the team who can hopefully resolve any problems that you're having. Hopefully you guys find this useful, and next week we'll run the FIJI for a quantification workshop in pretty much the same way. So me presenting the demonstrations first, and then you guys having free time at the end to go through using the documentation and get used to doing all of those different steps. Thank you very much.